Today we're going to talk about how to use mixed cash flows. We talked about the present value of a series of payments and the present value of a uniform annuity, and then cap that off with how to use that formula in capital recovery for loan payments and capital recovery of capital purchases. Today we're going to give a quick summary of the 4 factors that we have learned, and then we're going to talk about the adjustments for the number of conversion periods per year, and then learn how to use mixed cash flows, or how to use the 4 factors that we know to solve the problem. And we get to the capitalization factors. Okay, this sheet we're starting with the summary of factors. We have basically have 4 new formulas that we use when we're dealing with time and money. And if you look across the top, you see that we have titles for the present value, and we have a column for the future value. If we look at horizontally on the left-hand side, we have a row for single sum, and we have a row for the uniform annuity. And where those intersect, you can see that in the first box is our first formula, which is the present value of a single sum of money. Across from it, we have the future value of a single sum of money. Then in the bottom left-hand box, we have the present value of a uniform series, and in the last box, we have the future value of a uniform series. That gives us the 4 formulas that we'll be using in this class when we're dealing with investment. And as you can see from this sheet, they're not that complex. They're not even that difficult. The hard part is to understand where to use them appropriately. Also, as we get further along, if these formulas start getting difficult or hard to understand, come back to this chart and you can see they're really pretty basic. Now, I'm going to show some what I call a caveat or warnings. If we're going to use these factors, we have to understand what they mean. First of all, these factors are based on a compound interest rate. Okay, interest earning interest. These factors are not based on a simple interest rate, but a compound rate. Also, the interest rates, whether we're compounding going from the present to the future or discounting going from the future back to the present, these rates that are embedded in these formulas on the previous slide are constant. And that's a big assumption that you have to be aware of, because as you know, interest rates change minute by minute, just as you do cattle prices or corn prices. To simplify the arithmetic, we are assuming that those rates are constant throughout the horizon that we are using. Now, obviously, you can relax that assumption, but the problem becomes more complex. Also, these uniform series present value factors and the uniform series future value factors are only valid if we're using end-of-period cash flows. It turns out that we could, and in fact, you probably have done it if you've taken another finance course, you can actually come up with similar factors that can be derived for beginning of period cash flows, and they're usually called annuity due factors. They're just like the USPV or the USFV factors, except their arithmetic is based on the cash flows begin at the beginning of the periods and not the end of the periods. Instead of adding 2 more formulas to your toolkit, I'm just going to show you how to look at the problem so you can use the USPV or USFV factors, even if you have beginning of the period cash flows. Also, for cash flows that have uniform annuities and a single sum amount, you can mix these factors to solve the problem. You can use the annuity of factors alongside the single sum factor, depending on the problem. And we will go over some problems today that require the mixing of the factors. First, I want to digress just a little bit and talk about how to adjust these formulas when you have conversion periods per year that are not annual. And we've already talked about that in different forms, but we haven't formally discussed it, so we're going to digress just a little bit now and talk about that. First of all, the notation, let's let the I represent annual interest rate. Let's let the uppercase Y represent the number of years, and C represent the conversion periods per year. That's how many times the interest becomes part of the principal during the year. If interest is converted to principal every month, then there's going to be 12 conversion periods per year. Let's also define this R to be our per period rate, and we can get the per period rate simply by taking the annual rate and dividing the number of periods per year, or the conversion periods per year. And let's let n represent the number of periods, and we can get the number of periods by multiplying the number of years by the number of periods per year. To illustrate this, let's look at this chart where we have the conversion period, this compound period. This R is the rate per period, and n is the number of periods. And this R is calculated by multiplying the annual rate by conversion periods, and the number of periods is obtained by multiplying the number of years by the number of periods. So in this particular problem, we're assuming that the annual rate is 12%. And we're also assuming that there are 4 years in this time horizon. If the conversion period is 1, that means the interest accrues for the full year before it becomes principal. And so we say that that interest is compounded annually. We then calculate the per period rate by dividing the annual rate of 12% by the 1 conversion period per year. So per period rate is 12%, and the number of years is 4. But if the conversion period is 4, meaning that every 3 months interest becomes principal, there are 4 3-month periods in the year. So the conversion periods are 4. And we call that quarterly. It's compounded quarterly. To come up with the quarterly rate, we divide the annual rate by 4. 12 divided by 4 is 3%. So the quarterly rate is 3%. And how many quarters are there in a 4-year period of time? If there is 4 per year, then you're going to multiply 4 times the 4 years, and you would get 16 quarters in a year. If there is 12 conversion periods per year, meaning every month the interest becomes part of the principal, we are compounding it monthly. And what is the monthly rate? If the annual rate is 12%, we divide by 12, and we have a monthly rate of 1%. And how many months are there in a 4-year period of time? Well, obviously it's 4 times 12, which gives us 48 periods. In this process, really quite easy. If it says compounded monthly, you're going to divide the annual rate by 12 and multiply the number of years by 12 to get the periods. So it's that simple. Okay, let's test our knowledge of this, and we're going to look at a problem where we're going to deposit $10 in our bank account, and we want to know how much is going to be in our bank account in 2 years if it earns 6% compounded monthly. Now when you look at these problems, you have to look at, is this compounded annually or is this compounded monthly? You have to look at what is this rate, and it's tradition that rates are quoted as annual rates. So unless it specifically states that it's a per period rate, monthly rate or quarterly rate, if it says 6% compounded monthly, the 6% is an annual rate, not a monthly rate. So don't get confused with that. The rates are going to be quoted as annual rates. Now, how do we solve this problem? Well, first of all, recognize that the monthly rate, the per period rate, we're simply going to divide the annual rate of 6% by 12 to get 0.5%. In this particular case, the monthly rate is 0.5%. Then we multiply the number of years by 12 to get the monthly period. So we're talking about 2 years, so we're talking about 24 months. If we look at this on the timeline, our timeline changes a little bit. We still have our line. We're starting at time 0. But what are the number of periods? The 2 years have to be multiplied by 12 to get us to 24 months. Now when we look at, we're trying to see how much is in our bank account at the end of the 24 months, notice that we subscript that now 24 instead of 2. Because we're looking at the value in our bank account at the end of 24 months. And for the rate, instead of just quoting the annual rate, we're going to divide the annual rate by 12 to give us 0.5% rate. And now look at this in terms of which of the formulas. Think back of the grid that was presented at the beginning of the class. Which of the 4 formulas are we going to use now to solve this problem? What's the unknown? Is the unknown a future value or a present value? We're trying to solve for the future value. Is this a series of payments or a single sum? So we're going to use the future value of a single sum. The present value is 10. Notice in this case that the rate is not 6%, it's 0.5%. And notice that this is compounded 24 periods, not 2 periods. So in our calculators, we would put 24n, 0.5% I, $10 for the present value, zero out the payment, and compute the future value, and it comes out to $11.27. Now, the first question that I would ask is, if you plugged into your calculator 2n and 6% I, would you get the same answer? The answer is no. And the next question is why not? Because if you compound in monthly, what are you getting? You're getting interest on the interest quicker. Let's say that you have $1 million to invest for retirement, and you have the opportunity to put it in compounding annually or compounding daily. Which would you do? Okay, you do it daily, and let's see what the difference would be. You're looking at a period of time of 40 years. You're starting today putting $1 million into a savings account, drawing 10%. The red line represents if you're earning interest compounded annually. The green represents if you're compounding daily. And so in 40 years when you go to retire, if you put your money in compounding daily as opposed to annually, how much more money do you have at retirement? $10 million. If you put $1 million in, the difference between compounding daily versus compounding annually would be in the tune of $10 million. When you start dealing with compounded annually or compounded daily, or as you go through time, it can make a big difference. Now, notice that for the first few years, do you see much of a difference? Not much. But when you go out longer periods of time, there's a huge difference.